Today, it's a great pleasure. This is, and she doesn't even know it, she's one of my favorite speakers that we've ever had here. And part of the reason is because, you know, I'm a biologist, and I think I'm a pretty good biologist occasionally on good days. But I love geology, and I want to know more and more. I never seem to have the time to keep up with it. And this next speaker has helped me in ways she doesn't know, just in a couple of the talks she's given in the past here for us. She makes it so understandable and allows it to be so exciting. When I taught biology, I was flattered. At one point, several of my students came up and said, "Well, you make biology so exciting." And I said, "No, I just don't get in the way of it. You know, that's the trick." And so I always sort of think of that when I hear this next person talk, because she doesn't get in the way of geology, so really illuminates it for us. She's been employed as the geologist for BLM's Cody Field Office since 2006. That covers the northern part of the Bighorn Basin. She's also the owner of an independent consulting firm, Hurley Geological Consulting, and she's been operating that since, I think, 1996. In there, she has quite a varied experience, and I love to go over this each time, because you know her and you say, wow, I can see her doing most of these things here. She was a mudlogger on wildcat oil wells in Utah, Nevada, Idaho, Colorado, and Montana, and over the last 31 years she's worked in the arenas of, are you ready for this? There'll be a quiz after this one. The arenas of synthetic fuels research, mining and reclamation, oil exploration, pipeline construction, geological site investigations, mapping, environmental regulation, water rights, which keeps her, by the way, pretty busy most of the time, water quality sampling, surface and groundwater hydrology, watershed and land use planning, and I just ran out of space here on the page. So she's been involved in really just about every aspect of hydrology and geological work, most of it here all of it here in the West, I think, and most of it here in the Bighorn Basin. She recently just completed 8 years serving on the Wyoming State Board of Professional Geologists Licensing Board. So please welcome, with her talk today, Whispers in the Rock, Stories from Northwestern Wyoming Strata, Gretchen Hurley.
Oh boy, thanks, Chuck. That was pretty incredible. Yeah, it's really an honor to be asked to come back here again and speak before you for the Draper. I think the last time I was here was 2010, and it's always a lot of fun to put together a talk based on a field that I love, geology, which of course is based on so many others in the scientific realm. I was asked to give this talk this year, pick a date and then pick a topic, and I gave it a lot of thought and decided that I would talk today about the things that we really don't hear that much about. They're very important geologically, but they're not in the news much. And the more subtle aspects of the rock record. And Chuck's talk, your Sage in the Wind title, inspired me. When he talked about, I believe it was eagles and golden eagles and their habitat. And so I decided that I would name my talk Whispers in the Rock, the stories from the strata of the Bighorn Basin, mostly the northwestern part of Wyoming here. And just try to share with you some of the amazing features of the strata out there that you might not hear about otherwise, but also kind of because so much of what we learn about and hear about in talks in the scientific realm is about the big, fancy, bold stuff. And as a geologist, and I work in applied geology, I don't get to go out and do research, which is like the nirvana for most geologists, to go out and explore new things and discover new things, which we'll talk about some of those things today. But I work with my colleagues in applied geology, mostly land management, and basically taking the things that other folks learn and applying them to the real world. So it's fun to be able to talk about what other people are learning and doing out there in research. A lot of it has to do with these charismatic, predatory dinosaurs like T-Rex and Velociraptor and stuff. Today we're not going to get into that at all. Here are the goals of my talk today, and it's going to be very laid back, very informal, not hyper scientific. I want to share with you some of these more subtle geological things out there, hopefully with a little bit of humor and informality. as well as encourage you as individuals to, try to slow down your life a little bit. Maybe quiet. If you're like me, it's just constantly everything going all at once. And we've got this beautiful world out there, and one way to really de-stressify, if you will, is to just take some time and learn about these different layers, these strata out there, and just get out there where it's quiet, where all you can hear is the wind, maybe an eagle flying overhead. That's for Chuck. And just, maybe some crickets and birds, and just enjoy the strata, because they really have a lot to share with us. I wonder if the lights could be turned down at all for the slides. It seems really bright. Maybe this is your normal lighting. Just seems really bright. And once you listen to my talk today, you'll get some ideas of where you can go exploring safely outside, seeing some of the strata. And then once you get a feel, oh, that's so much better, thank you. Get a feel for some of the low-key things that the rocks have to tell us, namely some of the things we're going to talk about today: sedimentary structures, trace fossils, things like that, the more subtle evidence of wind, water, life, and combinations of those. And maybe it'll make you think a little bit about ancient environments and how we're very similar to our current situation on the planet, because the ancient environments that are preserved in the rocks are really analogs for what we're seeing today, and vice versa. So what we'll be looking at today in my talk, and I'll try to keep it clipping along because I've got quite a few slides, these subtler whispers in the rock today, things that you might not have even thought about much going through your daily lives. Those little things add up and help us get a better understanding for the bigger picture, not just geologically, but in Earth system science as well. I'm going to wrap up my talk today with some research that's being done. It's got international implications on climate change. So I'll be wrapping up the talk with that today. But really what it is the artistry of the rocks. Nature, of course, provides some incredible artistic value. And so in sedimentary structures, which we'll be learning about today, trace fossils, and other things that we learn from the rock record, we can extrapolate from those subtle messages some very important things out there on the ground and in our lives. Brief review, we're going to pretty much focus today on the sedimentary rock record. We won't be getting into a lot of other hard rock type geology today. Why is that? Well, because most of these whispers, these subtle features, are found in sedimentary rocks. Basically the rocks that are formed of grains cemented together, or chemical deposits that are precipitated over time and lithified. Some of the sedimentary rocks are very fine-grained, some are coarse-grained, like conglomerates and sandstones that you see here. But it's these sandstones, siltstones, conglomerates, and shales where we get these really finely preserved detail that allow us to reconstruct ancient environments. This slide here is one of my favorite slides of all time. It's just down the road near Grass Creek. But anytime you're out hiking around, and who likes to get out and hike? Let's see a show of hands. Get out and do it regularly. Excellent. That's a good ratio right there. Anytime you're out poking around in the hills and you see these kind of deposits, big rounded cobbles, kind of with a matrix of finer grained sediment, you can say to yourself, wow, there must have been an uplift or some kind of gradient change, because the only way these big rocks could be transported and deposited is by fairly good-sized rivers draining mountains. And so basically, these are indicative of uplift and fast-moving water. They have a lot to tell us, these conglomerates. And notice how the conglomerate layer is overlying a floodplain mud. The channels that deposited a lot of these big conglomerates meandered over the muds that were previously deposited in the floodplain. We see this today with the Mississippi River and other big river systems. Those channels migrate and will bury what was previously a floodplain deposit. So you'll see that in the rock record a lot too. And a lot of the talk today will focus on these finer grained sedimentary rocks, our shales and clay stones, a super, super fine, almost powdery sized sediment that is cemented together. Those are the sediments that really capture some detail out there as far as ancient environments and ancient life forms. So basically, one of the first things you learn about in stratigraphy and sedimentation in college is sedimentary structures. And they form in soft sediment. So they form, over short periods of time. But at any time in the geologic record, really, when you've got sediment being deposited, not eroded, there's a big difference. We're currently in a period of erosion as opposed to deposition. But basically what you've got preserved in the rock record are ancient evidence of winds, waters, various types of waters, ices, and owls. Well, not just owls. Many, many animals have affected the sediment over time, invertebrates, vertebrates, and of course, people. But I like that little owl. This is kind of a graphic of the different types of sedimentary structures, just very simple, easy to spot out there in the rock record that are some of the whispers that I'm talking about today. The subtle things we just really don't think about that much, but that are out there talking to us if we would just listen to them. We've got, it's kind of hard to see some of the words there, but cross beds. Oh, well, my words faded out pretty badly, but that's okay. Cross bedding would be the left upper, and then graded bedding is another one that we see, which I just kind of showed you with the conglomerates. Ripple marks, and we see those preserved in rock. Various types of ripple marks can tell us a lot about the environment. Was it a river? Was it an ocean? A beach? Mud cracks, which kind of look like the honeycomb here, which tell us a lot about climates and weather patterns in an area. And I believe the next one is nodules and concretions. These are formed after the main bed of rock formed, usually by groundwater moving through a saturated rock unit and concentrating minerals like around a nucleus, maybe a fossil or a pebble or an owl. No, just kidding. Making a nodule. They take a long time to form, so we'll show you some pictures of some of those today too. Some of those you break open and you get the beautiful crystals, geodes, that you see from a lot of good ones from Brazil. So again, just a little preview of what some of these will look like. And then we're going to launch into a discussion of 3 specific formations here in the basin that inspire me whenever I go out geologizing. Current ripples, which you see here. Okay, good, that one didn't wash out. Current ripples, everybody probably seen these in their travels, actually lithified into the rock. You also see them in current day hydrologic environments along beaches, along river shores, etc. Current ripples are distinguished by kind of asymmetry. One side is going to be steep, and one limb will be a little bit more gentle. And the steep side is always going to be pointing downstream. So if you find some rocks with current ripples, you can actually determine the paleo flow direction of that stream in which that rock formed. Wave ripples, on the other hand, are more symmetric. If you visualize a lake or kind of an enclosed body of water, when water moves across the surface of that body, it's not traveling in a current, but it's oscillating up and down like this. And so a wave ripple is going to be symmetrical as opposed to asymmetrical, like a current ripple. So you find wave ripples, you think, oh, that was formed in a lake, or perhaps a sea, or maybe a little swamp or playa environment, or an ocean, along an ocean. Wind ripples are also beautiful, and they tend to have so many different forms because wind, playing over the surface of the earth, either now or in geologic time, it shapes some incredible, beautiful landforms, big dunes, huge Barcan dunes like in Saudi Arabia or the Sahara, all the way down to small ripples, to several inches in width. Mud cracks, this would be a current day lake bed that is dried up, usually form in fine-grained sedimentary rocks that have moisture, which again, of course, evaporates, and as the water evaporates, the sediments contract. They dry out, desiccate, and then the cracks form in a pattern dictated by usually by the type of clay or sediment it is. When it's preserved in the rock record, it looks like this. Frequently, the mud cracks will fill with other sediment. And so if you find preserved mud cracks in the rock out hiking around, you can infer that that was a dry lake bed, perhaps, or a swamp that dried up. And again, it has a story. Maybe there was some interesting life forms that lived in that water body. Maybe they're preserved right there in the mud cracks. Maybe there's raindrop impressions there, preserved in the mud cracks. Maybe there's tracks. So lots of things to be told by the rock record, by the sedimentary structures. One of the most beautiful, intricate features that you find in the sedimentary rock record are called crossbeds, or cross-bedding. Another term for that is foresets. But each one of those layers you see in that would be a gorgeous lake deposit with the hammer for scale, represents an episode of deposition of sediment. And each little laminae or layer that you see there, kind of like wood grain, if you will, may have trapped some unique event in some animal's life. You know, an episode of predation or reproduction or what have you. Footprints. You see that beveled surface at the base of the hammer handle? That represents an erosional surface where you had deposition of sediment interrupted by erosion of sediment, removal of it, maybe by a big flood current, water flow through there. And then that ended, probably a storm event, and deposition continued above. So that's a story right there, just by that one contact. And then it looks like there's also a little bit of, maybe a little faulting in there, just a little bit of shifting of the sediments relative to one side to another. These, here in the rock record, or the rock outcrop you see before you now, are what are classic called foresets. And basically that is just one side of a big dune or ripple feature in the rock. It's not rock that's been uplifted and turned over. It actually was deposited in that form, in this slant, if you will. And that's called a foreset. You see those a lot too. And cross-bedding, again, shown here as beveled. It's called beveled cross-bedding or foresets, where the one dune or ripple event was deposited, again eroded and beveled off at the top, and the next depositional event was horizontal on top of that. So, just very subtle things that the rock record can tell us. Just are willing to look at it and study it. The next category of things before we launch into the Cloverly Formation, which is one of the specific, most beautiful deposits in the Bighorn Basin, just a few shots of what are called trace fossils. Trace fossils are the opposite of body fossils, and here you're talking about biological agents affecting the sediment. It happens again when the sediments are soft. Worms can't really chisel through hard rock. So, you know, this is basically representing here a hand sample of all kinds of different sizes of worms that have moved through this particular sediment, which is from the Gros Ventre Formation, and kind of left behind trails and other stuff that worms do as they move along. All different kinds, sizes of worms, from that little skinny guy all the way up to the big, more adult-sized worms right there in front of you. And again, these tell a story. Other kinds of trace fossils. And when I say trace, it means evidence of an animal that was in the area at the time of deposition, at the time of rock formation, but not evidence in the form of a tooth or a bone or a claw, which would be a body fossil. Trace fossils are other evidence of animal life, such as track sites, trails of whatever the animal was that left a trail behind, the burrows that they make, while either escaping a predator perhaps, or hunting for food, or looking for shelter. All kinds of different kinds of burrows. Tunnels, same thing. And bioturbation is a fancy word for just digging in the sediment, for whatever reason. I love this shot down here. Is basically an animal probably diving for cover. And you can tell he was going into the sediment, can't you? Because he's dragged some of the darker gray material behind him as he scurried into the sediment. Probably looking for shelter or cover from some predator, but leaving behind a really intricate pattern. And there are folks that would be able to identify what animal that was that did that. the ultimate, in my mind, the ultimate trace fossil are plant fossils. When they're preserved in fine-grained rock, every single vein is preserved. Sometimes even the stomata, where the leaf respires or makes its food photosynthesis. That's what I'm trying to say. Yeah. Sometimes those features are preserved as well. And the Bighorn Basin is a treasure trove of plant fossils. So in my opinion, they're just the ultimate trace fossil, because really you don't have the leaf anymore. It's long gone. But what was left behind, frequently in volcanic ash or shale or siltstone, very fine-grained rock, is a perfect impression of whatever that leaf, stem, seed, cone, needle, whatever the plant was, roots, even sometimes trunks, left behind in the rock record. So these are the ultimate, I guess I've said that already, haven't I? Trace fossil. All right, so with that little review, we're going to launch into the talk now. We're going to first talk about several, the earliest Cretaceous formation in the basin. We don't have time to go over the whole geologic section, but as you can see from this column, this is what's called a stratigraphic column. Geologists use these every single day. And every area has a different column depending on whatever rocks and formations and work's been done in that area. For our area, where you're sitting right now, in the Bighorn Basin, this is the column, and it is thick. We've got a huge number of formations here represented in the rock record that haven't been eroded away. They're still here to be studied, thank goodness. And a lot more than a lot of areas have. So that's why Wyoming is so rich geologically. We've got most of our sedimentary rock record here still, cropping out in different ways along the basin. We'll be starting off here with the Cretaceous Cloverly Formation, which formed about 120 million years ago. And some of the features that it has to offer, just pure fun, okay? We're just gonna have fun from this point out. I just wanna show you some of the cool things out there. And then we'll look at some of the neat things about the next formation up, one of the next formations up, called the Mowry Shale. And these two formations are awesome because one is a river deposit that formed on land. Just like rivers today that are flowing across land or depositing sediment. That's how the Cloverly formed, and yet, just 20 million years later, the whole area, the whole state of Wyoming was covered with an ocean or a seaway. And that's recorded in the rock record too. So you go from a terrestrial environment to an ocean environment. If there's time, and I hope there is, we'll talk about the third set of formations, which is called the Eocene, or the Fort Union-Willwood contact, called the PETM, which we'll get into that. That's the one that has to do with climate change implications. So we'll clip right along here. The Cloverly Formation, again, was deposited by rivers, and so you're gonna see bright colors because a lot of the sediments were oxidized. The minerals they're in were basically changed into beautiful colors through oxidation patterns, rusting, if you will. And it's a very multicolored, beautiful formation. But looking at it from this picture, you wouldn't know. It's just pretty to look at, but you wouldn't know how cool it is until you actually get out and hike around. And this is the one, if you're in this area at all, I would encourage you to come by the BLM office, and we will show you some neat hikes and exposures where you can go out and just enjoy the solitude and the quiet out there and the colors and the works of art to be seen. Just a quick map of what the planet looked like back when the Cloverly was being deposited. Africa and South America were united. They hadn't split apart yet. We had an inland sea called the Sundance Sea that was pulling back off to the north, which you'll see on the map on the left there. And the Cloverly sediments were coming into that basin that was left behind the Sundance Sea. Again, this is about 120 million years ago. And filling that basin with sediment, different types of sediment, sandstone, volcanic ash slurries, which we're going to get to here shortly, and then more sandstone. So it was kind of like a sandstone in the bottom, volcanic ash in the middle, transported by rivers, and other sandstone on top. But I just wanted you to see what the planet looked like back then when this formation was being laid down. Here is a lovely exposure of the Cloverly. And you can see that it's just multicolored. This is over north of Grable. And it's been stratigraphically divided into three members. The lower Pryor Mountain member, the middle Little Sheep member, also known as the lavender beds, which you're going to hear that term, and get to handle some of the rocks from those in a moment. And then the upper Himes member. So these beds represent, just want to make sure you can see it, huge, wide, meandering river systems that were transporting sediment from highlands, which were located to the west, over in Idaho, what's now Idaho, and what's now the overthrust belt, coming off of the overthrust belt, which was forming at the same time. And that's down by Evanston and over into Utah on the Wasatch Front. So where we're sitting right now was a river basin that was being basically buried by these sediments over time. And bringing in interesting things that we wouldn't know were coming in, except that it's been discovered over the last several years about these interesting things that are being brought in. As well, this was habitat for dinosaurs and multiple kinds of creatures, reptiles, and so on. In the Cloverly sandstones, or the lower and upper members, we see all kinds of interesting sedimentary structures. You see all the ripples that we showed you. So if you just get out and hike around, you'll see these things out there right in front of you, and you'll be able to say, hey, that's a current ripple. I know what that is. A lot of the sediments are also reworked once they were buried and lithified and kind of burrowed into frequently by critters prior to that. But once they were lithified, a lot of them have been exposed to stresses, tectonic stresses and unloading stresses, and there's fractures and cracks that run through the rock as well. This is the middle Little Sheep member, an exposure of some of the beautifully sculpted mudstones and siltstones. I guess they're softer, so they're going to erode into a kind of a more sloped aspect. And this is over east of Grable, if you have a chance to go see what's called Devil's Kitchen. This is where that's located. Here's another really nice shot of it. It's a very small exposure, but you can drive right to it and overlook it from BLM access point. And you can actually hike out kind of on a peninsulas into it and down into it and just explore it. But you don't want to do it when it's too hot. But it's a classic exposure. Again, the various different colors, a result of different, pretty much levels of iron in the sediment, oxidizing over geologic time. We have, in the Cloverly, we have some really interesting dinosaurs. I know I wasn't going to talk about big megafauna, but I had to stick one slide in just to show you that not only is this formation beautiful to look at, but it yields some fascinating fossils of various early Cretaceous dinosaurs. Most notable would be Deinonychus, the predatory dinosaur, who is a forerunner of Velociraptor, who everybody knows about from Jurassic Park. In the ash beds, or the lavender beds as they're called, because they frequently have a very lovely kind of a lilac hue to them, we find treasures, kind of a rock hounder's paradise, if you will. Stuff you wouldn't even know was out there. Nodules. Again, these are not trace fossils, they're sedimentary structures. Okay, they're what we call secondary. They come along later, after the rock has formed, lithified. Groundwater moving through the sediment, moving through the rock actually at that point, helps to lithify the sediment and also concentrates usually silica or iron around, say, a nucleus of some sort. I've actually got some beautiful, well, the same ones you see in the picture up front, and after the talk, if you want to come up and see some of these lovely chert nodules, they're here for you to see. But for some reason, in this particular bed, the chert takes on almost a milky blue fluorescent color, and it's just really fun to find. The other really neat thing about the Cloverly, you wouldn't know it until you actually get out and hike around, and I've got some friends in here who know my passion for this thing. For these particular features are these wonderfully highly polished pebbles. They're just, big enough to fit in your hand, and again, I've got some samples up here for you to look at. Of all colors and many different rock types, weathering out of the lavender beds, typically. So if you're out hiking in the Cloverly and you're in that middle ashy layer, look down at your feet, and you're going to find these scattered all over the place. They come in all different kinds of colors and shapes, and they're just super highly polished. A lot of folks think, wow, there were dinosaurs in the Cloverly. Dinosaurs used to swallow stones and use stones to digest their food. I bet these are gastroliths. Anybody heard that term before? Stomach stones? Okay, Jennifer. Yeah, gastrolith, gastro meaning stomach, lith meaning stone, stomach stone. Actually, some of these kind of polished rocks you find, especially in the Morrison Formation, are gastroliths. And these look a lot like gastroliths, but people say, hey, they are. You know, there were dinosaurs there, so it makes sense. I wanted to learn more about these rocks. It just seemed so anomalous. So I turned to the internet. I just had to know more. And right away, when I Googled Cloverly pebbles, gastroliths, I found something on eBay. Someone up in Montana has found a way to make money off of these things by saying that they're gastroliths. Well, they do look like stomach stones. They're very shiny. They almost have a waxy feel, supposedly acquired by being inside the stomach of a dinosaur. And they're the perfect size. And they were collected in the Cloverly Formation, and they're selling for $7.50 a pop. Some of the bigger ones are selling for $35 a pop. But there's a problem. They're being sold as gastroliths, but they're not. Remember how I said to remember the ash bed? Well, think about volcanic ash and what that is. It's not something we think about every day. But basically, it's fine grit, okay? So if you have pebbles that are picked up from, say, the overthrust belt, cliffs over there, you know, river rock, whatever, and transported hundreds of miles northeast into the Bighorn Basin, are those rocks going to get polished just a little bit? You darn tootin'. And some of them are going to get hyper polished, and some of the ones I've got over there are so shiny you almost need sunglasses to look at them. So I got to poking around a little bit more on the internet and found this seminal paper, Hyperconcentrated Flows in Gastroliths. Hyperconcentrated, and I want you folks to try to visualize a Dairy Queen blizzard on overdrive flowing across the landscape. Okay, that's what a hyperconcentrated flow is. It's about 50% water, about 50% sediment. So it's like a big slurry traveling across the landscape in these huge rivers. And that's what formed the lavender beds, essentially, during an early Cretaceous time. Enough to polish these pebbles in a beautiful way. And what they're called is extraformational. In other words, they came from another formation, were picked up by this event, and transported here into this basin and deposited. And we find them over here. And some people make money off them. But yeah, here's the highlight right here. They are not stomach stones. As much as folks would like them to be, they're not. They're just pebbles that traveled a long way and got polished to a high polish, basically. But they're beautiful, and they tell us a lot about the depositional environment and even the tectonics of early Cretaceous time, what was going on to the west. Okay, now, this may seem anomalous. But every good geology talk has to have a Far Side cartoon. This is one of my favorites. All right, it's good. Just patience. Just don't forget it, okay? We're going to talk about the Mowry Shale next. And the Mowry Shale is just a little bit younger than the Cloverly. After the Cloverly was deposited, interior seaway called the Cretaceous Interior Seaway moved in over the whole state of Wyoming. It came in from the north and it came in from the south through the Gulf and connected across the Rocky Mountain west. The Rocky Mountains hadn't formed yet. So this all predates the Rocky Mountains. It predates all the mountains you see around us here in Cody. This whole area used to be covered by a shallow seaway. How are we doing for time, Chuck?
15.
Okay, I'll make it quick. Basically what you've got is fine-grained shales and bentonite clays and all kinds of really nice fine-grained rocks preserving features. In outcrop, it doesn't look like much. It's kind of boring. It just looks like gray slopes. But where it's been exposed, and in this case, this is a bentonite mine. where we happen to regulate bentonite mining in the Bighorn Basin, so we get to get out there and see a lot of these neat outcrops. What you're looking at here is a bed of high silica shale dipping. So it was laid down horizontally in the seaway, and then it was uplifted. So it's dipping about 30 degrees off the horizontal. And the bentonite bed above it has been mined off, exposing the shale. And on that surface of that shale are some incredible trace fossils that we actually are working with Casper College now with some grad students that are studying those. But really fine, detailed worm trace fossils, these worms that used to live in the seaway. And also neat things like feeding traces, where you'll see just a line. This is all totally in the rock. It's preserved in the rock. It's not soft anymore. A line, probably where a Cretaceous fish, just skedaddled across the surface of the shale feeding. You can visualize it. You see fish doing it today in the ocean. And there it is, preserved in the rock. And that's Greg for scale. He's not feeding. But the coolest thing of all that we see on this outcrop are these unique kind of radial star-shaped patterns. And has anybody ever seen these before or heard of these? They're trace fossils. You know they have to be marine life form because it's in a marine deposit. That's what one looks like close up. Kind of like something poked itself into the seafloor, hunting something, maybe a worm. Well, turns out they're squid kisses. This is why I had the kissing joke. And yes, animals do kiss, especially when hungry. Who would know about this stuff unless you get out and we're actually lucky enough to be able to work in the Bighorn Basin, which is one of the very few places on Earth where this is found in the rock record. So it's a fascinating trace fossil. These were actually Cretaceous-aged squids, or related to today's cuttlefish, that lived and hunted in the early Cretaceous seaway and left their mark. All right, we are going to have a little time. I think I'm doing all right time-wise. Lastly, okay, we've covered two formations, and again, this is just fun, informal stuff. I hope you're enjoying it. But this last one is a little more serious and a lot more subtle. And it's taken a lot longer for these whispers to be understood. They're still being studied. The Paleocene-Eocene boundary, this is about 56 million years ago in the geologic record. Turns out that it is internationally significant now. It first started to be studied in the early 90s by folks all over the planet, geologists, geochemists. And now it has taken on a life of its own. What you're looking at here is Hart Mountain in the distance, way in the distance there, which is just north of Cody, a geological enigma in of its own. And in the foreground, basically the beds of the Willwood Formation at McCulloch Peaks. Why is this so important? I'll just let you read this. The contact between the Paleocene and Eocene is an analog for climate change, what's happening in the rock record. And that contact represents a time period about 56 million years ago. That's what's called the beginning of the Eocene epoch, the early epoch. And what geologists and geochemists are discovering now, and mammalian evolutionary biologists, if you will, is that at that time in geologic history, thousands of gigatons, that's 1 billion tons times thousands, of carbon, probably in the form of methane, which then oxidized into carbon dioxide, were released around the globe, causing climate change, a huge global warming period. This is natural stuff that took place in geologic time about 56 million years ago. And the whole event, which covered about almost 200,000 years of time, is preserved in the rock record here in the Bighorn Basin. There's only one other place in this, between North and South America. There are other places in Europe and Russia, but only one other place in Mexico where this thorough section of rock record that provides this data is available. It's down in Mexico. The other place is up here in the Bighorn Basin, where it's several sites. So we've got portions of our rock record up here that are so complete that the whole picture can be studied and seen. And the implications are huge. When this thing kicked off about 56 million years ago, and I'm still learning about it because it's fascinating, and it's also in progress. Scientists that are working on it, and there's dozens of them, are finding something out new every year. Stuff how this thing affected plant life, how it affected animal life, how it affected ocean current flow. It's huge, and it has implications going forward for us as well. This is what it looks like in outcrop, this whole zone. The drab beds at the bottom are the Fort Union Formation. Then you start to get into the reddish layers above it. That's when you're transitioning into the Willwood Formation. And so right there at the transition where you're starting to get red beds, that's the contact. That's where everything started to change, where the climate took a huge hit and got about 40 degrees warmer on average, 40 degrees than it had been prior. So you went from a kind of a temperate climate to a tropical climate over 15,000 years from this release of carbon, which is still being studied. That's what it looks like, and it's all complete. It doesn't look like a whole lot except red sediments, but the scientists are delineating and defining this thing, and that's what it looks like on the ground. And the only way to find this out is to get in there and dig. Dig, test, find, sample, collect, refine, come back and dig some more, year after year. And every year, the research gets more specific. Scott Wing of the Smithsonian Institution is one of our permittees at the BLM, Philip Gingrich, the University of Michigan. These guys are on the cutting edge of this research, and we're lucky enough to be able to work with them every year. This is Dr. Wing from the Smithsonian. If you get on the internet and just Google his name, you will find a wealth of information. But I wanted to show you this graph, because again, it goes back to the whisperings, the subtleties, the things you don't really hear about or learn about that I wanted to share with you today. If you look at his graph, you'll see that red curve. And you'll see some leaf samples that he's collected. And this is the coolest graph because what it shows you is that prior to 56 million years, you had one set of flora, I'll just call it a flora, that represented temperate climates, kind of what we're living in today. Then abruptly, the climate, well, over 15,000 years, that's pretty abruptly geologically, the climate got so much warmer, almost up to 40 degrees Fahrenheit warmer on average. That's a huge, huge change. Those leaf fossils that you see under the red curve are like Floridian flora. And they migrated up here from the south because it was too hot for the temperate flora, which vanished. The Floridian type tropical floras migrated up here, on the wind, via seeds from birds, just however they would migrate up here, and took hold over the course of from 55.6 to 55.8, which is about 200,000 years. And that's about how long it took for this whole thing to calm down geologically and kind of go back to normal. So about 200,000 years, we had this huge spike in heat, and that's called the PETM, the Paleocene-Eocene Thermal Maximum. If you're into science, it's fascinating, and I encourage you to learn more about it. And it starts out as subtle data that slowly but surely builds into a kind of a roar. I mean, this thing is important because it has implications for our time as well. This is just a cool slide of some of the leaves they found, some of the temperate leaves, just spilling out of the rock record. Again, but you don't find them until you get out there and start looking. This is what the planet looked like during that time. What's missing? It's missing at the ice caps. Oh, ice. There wasn't any. There was no ice caps because a feedback loop had started. Once the temperature gets to a certain point, globally, and the average is high enough, thresholds are exceeded, all the ice melts, it enters the oceans, it changes ocean currents, so a feedback loop starts in the ocean, and then you get this continual increase in temperature and warming, which is shown in the rock record over some of this newer research is showing that there were several PETM episodes, not just one. They're studying one called Elmo now, which is PETM 2. Yeah, so lots of refinement going on. But this is a really cool map of what the planet looked like at that time. We've got it all preserved here in the basin. So yeah, we're in geologically, we're in internationally significant basin for scientific research. This map is very important because it shows you those red stars that you see there, folks. Those are the best locations in the basin for collecting data on the PETM. All the other colored dots are significant fossil localities that help us refine that data. And this is a map generated by Dr. Gingrich, the University of Michigan, probably one of the foremost researchers. Heck of a good guy. Yeah, this is just his key, keying it out and explaining the different formations. I'm just brushing the surface on this. There's so much more that you can learn about it. So one of the cool things, I showed you some of the information about how plants changed during that time. And that's kind of what we're starting to see here, or would start to see if we saw these kind of major temperature changes here in Wyoming over time. We'd get a less northern flora and more of a warm type temperature flora moving up here, but mammals changed as well. The rock record is providing specimens of mammals that never before were seen in the rock record, but that all of a sudden, kind of geologically, all of a sudden showed up at that contact 56 or 55.8 million years ago. You start to see in the rock record the first horses, the first deer, and the first primates. They were not in the rock record prior. So this episode of warming triggered mammalian changes in the evolutionary record as well. I like this slide because it reminded me of horse whispering. But the PETM horse is this little itty-bitty guy. And there's several names. Cypherhippus was one that I found on the internet, but very small, but basically the same morphology as the big horse inside, After the PETM, the climate change episode of 200,000 years ended, as the Earth basically what was called recovered from it, with sequestration of that carbon that had been released, the horses continued to evolve into the animal we see today. Same thing with primates and how they branched off, and the same thing with the various types of deer. There's all kinds of awesome articles out there about not only the change in horses, but the geology itself during that episode, implications for the future, paleoclimate. It's something that started out as just digging and finding little subtleties, little geochemical signatures, little tiny teeth of horses, and has over time, over the last 20 years roughly, become one of the most important scientific studies today, and is studied worldwide. There are bastions of scientists studying it for terrestrial data, and whole legions of scientists looking at the same event preserved in the ocean records, in ocean cores, in the ocean drilling program. They correlate perfectly across the time frame. It's some of the best science that you'll see. This is just a little blurb about Elmo, the second PETM. And I would encourage you folks to read about this if you're interested in science and geology, because it blends all these wonderful fields together and helps us understand what's going on now. These are just some of the researchers that I wanted to thank in my talk, because it's a constant discovery, if you will. And you're going to be reading and hearing more about it. And our land use plan with the Bighorn Basin that we're working on now at the BLM, we're looking at trying to conserve areas where the PETM contact is exposed for future research. In other words, we would allow multiple use there, but we would put the paleontological value ahead of other uses. So we would try to preserve and conserve that going forward because of the data value. And that's part of what we do at BLM, try to balance it all. So in summary, I hope this was fun for you, and that it encourages you to get out, get away from our computers, get away from the news, from the TV, from the video games, and get out and explore this incredible planet that's right at our fingertips. Thanks for listening.